So Sean is not here. Shiv, Lam, Angie are here. Okay. Then we have Scott Nguyen.
Here.
Sean Nguyen.
Here.
Dung Dylan Pam.
Here.
Ayush Ramani.
Here.
Luis Ramirez.
Here.
Eric Rodriguez. Eric Rodriguez. Okay. Eduardo Ruiz. Eduardo Ruiz. No. Okay. Andy Shi. Young So.
Here.
Dylan Suen.
Here.
Johnny Trump.
Here.
Akash Thagarajan. Akash Thagarajan.
Here.
Okay, got you. Nicholas Thomas.
Here.
Jonathan Baladares.
Here.
Okay, got you. Jonathan Burgess. Jonathan Burgess, are you still here? No, why? Stephen Vasquez.
Here.
Rita Velasco.
Here.
Jiacheng Wen. Anthony Yu.
Here.
Jiwon Yu.
Here.
Justin Yu.
Here.
The three brothers? All the same last name.
Sadly not.
Kidding. Yeah, that's the same last name, exactly the same last name. Anthony, Jiwon, Justin. Cool, cool name. All right, so no brothers, huh? That's good. Even brothers is still good. I mean, there's nothing wrong. I had two sisters before. They're good.
Professor, you didn't call my name.
Who?
Steve Lamichane.
Yeah, of course I called your name.
Or maybe I came 1 minute late, I guess.
I beat you there. All right, so let me finish with you. I got you. Anybody else? Late comer? No, that's fine.
Hi, sir. My name is Zil Deora. I'm here.
Who?
Zil Deora.
Oh, Jill. Yeah, I call your name. Yeah. Jill. Last name was with the D. Yeah, I got it. Got you.
Yeah, Diora.
Yep. Got you there. No problem. Okay, so turn it up. Now we have 40 students. Supposed to be 50, and 10 disappeared, or I don't know, maybe absent, whatever. All right, so so we will go through the chapter. What chapter I was planning? Syllabus. Chapter 4, the functions. Okay.
Excuse
So-
me, Professor. Could you give permission to record again?
Oh yeah, sure, you can. So is that
You have to do it through Zoom.
have to do things here, or
Sorry, one more time.
can you do it now, or I have to do things here?
It says, please ask the host to give you permission to record.
Yeah, I give you the permission, but what was the other thing that we did the other day?
I think you have to go to participants and then find my name, which is Dylan Suen, and then click on more and then click permission to record or something like that.
So more. Okay, and then allow record local file, it says. What's that? Can you? Yeah, I think it's. Yeah, it says I got a message being recorded. Yeah, it's fine. All right, so we skip some documents from the other PDFs, but we will come back to that actually. So what I'm trying to do actually get you familiar with these symbols for these MIPS programming, and we'll come back and review this chapter again actually one more time, maybe a couple of times. You don't know. Time permits. So don't worry if you don't get some of this bit, because it's very different and different way to do things. And we'll learn more about this programming, but I'm not focusing too much on this, the MIPS programming for all these aspects, but the basic stuff we need to get it. So that's what I'm trying to go through. The basic stuff we need to understand and learn. So now look at this. I'm going to share this screen. Am I sharing now? No. This chapter 4 functions, the PDF file. I think it's already put it on there. So this is talking about functions. And stack and function call and return, parameter handling, register use convention, whatever. So in programming language that we have functions. So the function is what a piece of code for a specific purpose. And function has a name. We put name in any language, Python or Perl or PHP or C++ or Java. You have a name for a function and then you call that function. And function could be void function, and some other function could be value returning functions. So this MIPS also has that function thing, but how do you use them? How do you call them? It's very different, of course. So let's look at those functions in stack. So the first I have is stack. The stack is very simple. Last in, first out. Data architecture. So first in, last out. So you think about a kind of a box, let's say, only one side open, like the top side open and other side blocked. So if you have a box like that, and if you put books there, like let's say, box is like same size as the book size, like a little bigger than the book size, then you can't take it up. So it's the only way you can get into the middle of this book stack. You have to remove the books from the top, and then you can get into the book number 3, let's say, book number 4. So only operation you can do is from the top. Either you push on item there, or you pop on item from there. So you add an item, you do a push operation, and then if you're going to take one out or remove one, then you have to say pop operation. But both operation has to be from the top, because you cannot go in without removing the top ones. Okay, so that's the pretty simple data structure for this last in, first out. So wherever you put last, you have to take that out first. So that's the LIFO or LIFO, whatever you call it. Last in, first out architecture. Push to add, pop to remove. Stack in memory, it's kind of a similar way. So array of 32-bit words, of course, and then the register number 29, or the alternate name is register number SP, $SP, is a stack pointer. Contain address of the top item in a stack. So that's all it is. Stacks in most machines grow upward, of course, from high addresses to low addresses. Push, subtract from stack pointer, and pop, add to the stack pointer. How memory address space is usually allocated. See this here. Program text, static data, heap, and a stack. To push a 32-bit word from 23, register 23, to top of stack, you need to have add immediate $SP, $SP, -4. Why -4? Because it's actually 4 bytes. So 32-bit word is 4 bytes. So we go bottom to minus. If you go top, you're going to put more stuff, then you put a plus 4. So then you have a store word command, and then you have this $23 register, and then a comma, then you put this stack pointer in the parentheses. So this is, you do a operation, you take 23 to top of a stack, you have to do this operation. Alternate way to push an item, you store word, the register name 23, and then you -4 times stack pointer. And then we put this add immediate command, sp, sp -4. So that's another way. To pop item from top of a stack into $19, you load word and then $19, then you put this parenthesis $sp, and immediate sp, sp4. See, this time it's +4, not -4, because you're popping item from a top. So this, you add 4. So that's the command for this operation. And you go, so each line you times 4 bytes actually for that, because it's one row is like one line is 32-bit word. So each time you times by 8, 4, so it's 12, 8, 4, like this multiple of 4, because each line is 32-bit. That's what it is. And that should be good for this stack. I think I'm not carrying away too much. And then the function, we talk about function. So in C or C++ program, you have this function, integer power. So power is a function, like you put exponential things. And of course, in Python, you know that it's you write x times x, that's x to the power x. Put a star there. But in C or C++, you put integer main, so you declare a variable, declare a function actually, integer power, and then you put a parenthesis and you put a parameters there, int, comma, int. Both two parameters you need a base and you need a power, exponential number. So then you have this integer main function, and then you put integer x, p, y, q, just declare all the integers, and also results, integer also results, and then result equal to power x, comma, p. Function prototype for power. So then what is power means, you have to write it somewhere else. So the integer power, and then you write that, what power is supposed to do, and then you call it. In MIPS, first 4 arguments is A0 to A3 registers and return value V0, V1. Then caller is that the function you're calling from, and callee is the function you're calling. So that's the caller and callee. And then, so this is the temporary function, and then you write your power function and then you call it. That's not what in C, C++. But how about MIPS? MIPS, you do this. The jump and link POW, that's the function. And then return address 1, and then jump and link POW, return address 2, and then load immediate 10 to V0, this is called as terminate the program. And then you have to write what POW is, like POW colon, and then you have to write this POW function there. Return address after the jump and link instruction that we want to return to when function returns. Jump and link. So jump and link is a function, is a command in MIPS, is a symbol, is a L, and you use this $31 registers, $RA, return address. RA is return address. Go to label, any label you want. Jump register, they call it ZR. R is any registers. You can jump to any registers. Contents of R. PC is the program counter, is the contents of R. Then to return from function, it's a JR $31. So that's the register number. And When you go back to this MIPS commentator for Pow, you see that integer Pow, that's the C++, and then A0 arg0, arg1, result B0. Then you see this result equal to Pow xp means copy x into placeholder arg0, copy p into placeholder arg1, that's A1 and A0 register, and then call Pow. And the Pow, you use this move operation from S0 to A0, S1 to A1, and then jump and link Pow and move B0 to S2. So you see that it's quite different than C++, but you can do this. Here's the full program for that Pow. So you have a load 0T0, load 1 to V0, load immediate, and then if A1 is greater than T0, then branch exit. So the exit is jump register to RA, return address, and then have a for loop here for multiplication, and you add immediate, and then you branch less than 4. So you go to for loop again. So this is a loop. So this is how you do the power calculation in MIPS. So in MIPS, you do this like dot data, and then end1, let's say dot ASCII Z, and then you put this dot text, and then main, and then load is integer to all these variables here, and then you add, and then you add this, and then jump and link Pow, and then move V0 to S2, V0 to A0, and then load 1, immediate to V0, and then syscall, and then you go through this jump and link, syscall, and then you end the program. So this is the MIPS version of that power function. Okay, so it's an example how you can do this. This is the power, and this is the end of the program. Nested function, we're not interested in nested, so you can skip this. I think you delete it from this. And we're not interested in nested function, so just function should be good enough. So nested function is not necessary to skip that. Okay. But we have something else there. We'll be interested. Not that. String length, no. MIPS main program, string length, no. Bubble sort example. So in C or C++, this is like C++, the bubble sort, how it works. You have a sort function, and then you have a loop, and you swap things, and then you call the swap function from here. So swap function is separate here, and you can try it in using C++ compiler, and then in MIPS, how do you write that in MIPS? So you can try that. I think book has this example, and yes, the example for a MIPS program for sort, bubble sort. So its example is in 2.3 section. Check it. Nested procedure. Making decisions. Logical. Yeah, the book I have, it is not in 2.3, but it's in other chapters. Number, let's see. Maps available in instructional computer. Loops making decisions. Yes, in the book it has. My book is page number 92 actually, so it has the instruction how you can write the loop in MIPS, while loop, and also the other loop. Procedure computing, nested procedures. We're not interested in nested one, but it's a normal procedure. So stack pointer, program counter, stack, push, pop. Those are the instruction. This is 2.8 in my book. Procedure function. So that's example there. Nested one. And then, the bubble sort example should be in the book. All right, so one thing I need to show you, like how we can actually convert a MIPS code into machine code. So you see this, the MIPS code has all these MIPS symbols, like the here, all those. One moment, this a green sheet, and to look at the green reference paper. Let's lose that one here. So I'll put it on the island so you can download. So this is the reference paper. You'll see all this, the mnemonic, the symbols for this MIPS. So you need to understand, I'll read those and what this stands for. Right here, LBU, load, byte, unsigned. Load, hop, word, unsigned. LUI, load, upper, immediate. So you'll see that. So you have different instruction format. I think we'll look at the next chapter first, and then we'll come back to this. Converting MIPS code and machine code, because we have things to do. We have a lot of things to do there. And I'll test you on this too. So let's look at that next chapter. Next chapter is 5. This one. Machine language. Instruction operation, instruction format, assembly and disassembly, linking and loading. So that's the chapter we're looking at now. So the MIPS is assembly language. It's not a machine language. So the machine language is written only using zeros and ones. It's like a binary, just binary. You understand that? And MIPS is assembly language, very specific type for a specific type of CPU. And it only work for that specific MIPS CPU, not others. And then the assembler we have, that simulation environment, the Qt SPIM, that's only for MIPS. Any other code will not work there. The general format, you see that we have the operation name, and then RD is like a destination, and source and target. So RD, RS, RT. So any operation you have that, RD, RS, RT. So for add, we need three registers: registers D, registers S, and register T. So it's register destination register, source register, and target register. And then subtraction, also we need three registers, and add unsigned, also need three registers, and sub unsigned, also need three registers. Okay, you wish to for unsigned.
For sure.
All right, so now understand this, but here assembly language. Let's say this is the remainder operation, remainder, and then you need three registers. But then machine language, it's different. So this is the division one. You need two registers, and then you have the third register. So there, the results. MFLO is there. So MFLO is source and target registers, and that's MFLO means high and low. High RD means RD low. MFLO RD. So I'm keen on this RD and low and high, but we'll learn other stuff. We have the instruction format that we're interested. So this is the format. So here you have three types of operation format. So one is R format, J format, and I format, and they have different structure. Okay, you have a source, target, destination registers, and then function code or opcode for R format. Let me add the pad. I'm going to show you this format. All right, a similar thing you'll see on the green sheet. You'll see here, yeah, here, basic instruction format. You see that middle of the bottom of the first page. This is the first page, list reference data, and bottom of the first page on the left corner here, bottom left. You have R format, I format, J format. So let's draw this in here. So R format. So our format, what do we have? We have a 32-bit, total 32-bit. So we have all this 32-bit here. And then first, on our format, you see that the first from 31, you're going to start from this side. See, first we have this on the right side, 0 to 5 is the function code. Okay, so the 0 to 5 will be here, let's say 0 to 5 here. Call it function code. So it's 0 here. This is the register, the 32-bit. 32-bit. So that's the first one, function code. Then you have this, sorry. Then from 6 to 10, shift amount. 6 to 10, this is 6 to 10, visit, okay? So the shift amount, this says empty, let's say, shift amount. SH. And after that, you have this here. From 11 to 15 is the destination, RD. 11 to 15. 11 to 15. Sorry, 11. 11, 12, 13, 14, 15 is 5. So is RD, destination. So this is 0, 1, 2, 3, 4, 5. That's 6 bit. And then 6, 7, 8, 9, 10. 5 bit. And then 11 to 15. 11, 12, 13, 14, 15. 5. And then you have this 16 to 20. That's the RT, the target. 16 to 20 bit RT, the target register. So 16, 17, 18, 19, 20, 5. Total has to be like 32 bit, okay? No more than that. And then we have 21 to 25 RS. 21 to 25. So here, 21, 25. RS. 21, 22, 23, 24, 25. That's 5 also. And then I think it's 6 bit here for the opcode. Opcode 26 to 31. 26, 27, 28, 29, 30, 31, 6. So total is 30 bit here. Let's add it up. So 120, yeah, 30 bit. So that's our format. Now if you're given a machine code and ask you to translate into the MIPS code, how do you do it? You use this format. First, you figure out like what format is this, and then you follow this bit and convert it to binary, decimal, or hexadecimal, and that will be your machine code. All right, now, so this is one R format, it's like this. How about the I format? I format structure is different. I format is different. Okay, let's draw this same thing, 32 bit. So it says 32 bit here. Now, if you look at the green sheet for I format, immediate 0 to 15 is immediate. So 0 to 15 is kind of here. So 0 to 15 is immediate. And then you have RT and RS. 16 to 20 is RT. 16 to 20 is RT. And more. 21 to 25. 21 and 25 RS. 21. 25. Yes. There is no RD here. See that? And opcode is 26 to 31. 26, 31. Opcode. So this is opcode here. Like operation code. What kind of operation is this? So this is the structure. So it's total 32 bit. Okay, total 32 bit. If you count it like 6, and then this is 5. Is it 5? 20 and 25, 21, 22, 23, 24, 25. Yeah. And 16 and 20, 16 and 25, 5. Then it's 15 here. 15 or 16 here. 16 here. From 0 to 15 is 16 bit. So this is it. So you have 16 plus 16, 32 bit total. And then J format is more simpler. So you have 32 bit. So you have 0 to 25 is the address. 0 to 25. Address B. And then you have just that opcode, 26 to 31. Opcode. So this is the format for R, I, and J. So you have to, from a given example, you need to figure out that what format is this instruction in, and then you can actually convert it to MIPS code to binary, or machine code, and machine code to binary. So that's our job actually, to learn how to do that. But now let's go back to the slide. Let's see what they have here. So this is the R format. So you see that the function code is 11, and target is destination is 5 bit, and target is 5 bit, and source is 5 bit. And then opcode is 6 bit. So this is in binary, even 0000. So most of the R format, if you look at the green sheet, where is the green sheet? Right here. Now this will make more sense. Okay, so you have these symbols and you have this format. The add is in R format, so you need 3 registers: target, source, destination. Okay, and then you have this function opcode / function code is in hexadecimal. So you have a opcode is 0, function code is 20 hex, and then add immediate is the I format. So you have this source and destination, target, there's no destination here. And then you have this, the immediate bit here. And it doesn't have opcode, it has a function code, you see that 8 hex, okay? And then add immediate unsigned, also I format, and it has different function code. So with this function code and hex code, you figure out how to translate from MIPS code to machine code. So we'll see that in a minute. So all these symbols, the operation has a specific format and is given here. ORI is or immediate, and it's I format. SLT is a set less than is R format. Set less than immediate, I format. Then we have this SR, SL, SLL, SLL, shift left logical is R format. And SRL is shift right logical is R format. R format means you need to have 3, you have like 3 registers, and you have opcode and function code. So normally add, sub, and all this operation has R format, and they are opcode is 0. So most of them will see the opcode is 0. So the R format, opcode is 0. The first one. Now, I have a question here. Like if the opcode is 0, then you see that the different kind of application has same opcode like 0. So like here add, also opcode 0, and add unsigned opcode 0, and operation also opcode 0. then how do you figure out which one is add, which one is sub, which one is other operation? From the function code, So they're different. For add, function code is 20 hex. And you see the for AND, function code is 24 hex. Okay, so it's different. And even the other table here is given actually. So binary, decimal, and hexadecimal. If you have those hex numbers here, then what it means in binary is already given there, like DC4 in ASCII, but in 14 is the hexadecimal. And then in binary will be 010100. So it's already there. So you can just use that binary code if you want to use binary code, and decimal number also there. So you can use this table too. And the other table here is very significant because this is the register number in terms of the alternate name of the register. And this is the actual number of registers. This 29 is the stack pointer. So $SP, if you have $SP, then you can write 29. 29 in decimal actually. This is in decimal. This number is in decimal. So you have to convert it into binary if you want to put it into binary format. All right, so let's look at some examples. Let's follow through these. So this first. Here it is. So we have a AND operation. Focus on this. Register 23 is the destination. And then I have this register 22, register 13. Now, which one is RS, which one is RT, and which one RD? You figure out from the green sheet. So in the green sheet, for add operation, you see here, for add operation, see the first one is destinations. And the second one is source, and third one is target. RS, RT, RD. So if you go back to the example, this is RT, this is RS, this is RD. Okay, and this is an add operation. So when you convert it from this MIPS code to machine code, this is machine code. So add $23, $22, $13 is actually same as 00000 10110 01101 10111 000 0010 0000. So this is exactly the cancellation from this MIPS code to the machine code. You getting it? Sometimes you'll be given this MIPS code. You have to translate it into machine code. Sometimes you'll be given this machine code and you translate it to MIPS code. Using that green sheet, you have to learn this. And these numbers in binary, but we can write in hexadecimal as well. So still same. Okay. So here, list of arithmetic and logic instructions, register operands only R format. And you can see that from here. Just a list of operation. And now, it's a different kind of operations examples here. You see that add I, like add immediate, RT, RS, and immediate bit. So that's the I format. And I format, you know, that is you have only source and target, and then you have the immediate 16-bit. So if you given a number like that, you can translate it into machine code easily, like this, following this. So the I format, you have opcode 6. So the first 6 bit is opcode, and then next 5 bit is source, register, and the next 5-bit is target register, and next 16-bit is the immediate bit. Okay, so if you have this like ORI 23, register 23 and 13, so RS is 13 and RT is 5. So this is the I format, and this is the operation formats. If you see ORI, the first one is RT and the second one is RS. But here, RS is the first one and the second one is RT. You see that? You have to follow this ORI here. ORI from here, if you see that here. RT first and then RS. RT first and then RS. See here, RT first, then RS in this operation. But in the format, I format is RS first, then RT. So you have to notice, follow that when you convert this MIPS code to machine code, because when you put it in machine code, the first one is not RT, it's RS. So it's RS is this. So 13 will be first, and then the $23 will be here. Now, interesting question is that here we have $23, okay, RT, but here RT is 10111. So why did they get this? This is register 23 and this is 10111. Why did they get that? So using this green sheet, so you go back here in this paper here, register 23 here. Register 23 is $S7, basically. This is 23. Register 23. So register 23 is in, so that's in decimal. So how much is in binary? So we go to this sheet here, 23 in decimal, here, 101111. So 01. So because they make it 6 digits, so you put a 0 there. But actually it's 101111. So if you go back here, you see that 101111. So that's 23. 5 digits. So you put 101111. So this $23 is basically this in binary, and this is a register, actual register. But if you don't have this actual register, instead of $23, if you were given this, if you're given $S7, it's same. So $S7 instead of 23, then you can see $S7 stands for actually 23, register 23, register 23 in decimal 23, and when you convert it in binary, it will be this 10111. Are you getting it? And this is hexadecimal number, 2x9876. So hexadecimal, when you convert, remember that when you convert to 4 digits or whatever digits, you put it from the right. 6 is 0110, 7 is 01111, 8 is 1000, 9 is 1001. So you just place this binary bit here, that's 16-bit, that's the immediate bit. So
I have a quick question.
Yep.
For the format, is it always like given? So then would it be like I or R or F at like the end of the method? Because 0x9876 stands for like the I format, right?
Which one? Second?
Like
last
how the for the example or ORI if we're looking at the hexi.
So, yeah, ORI, and this will be given.
Yeah, okay.
When you see that I means is I format.
Oh, so that's where the I is. Okay. Okay.
So if you see this immediate thing, then you'll see.
I thought that the last digit or the last one, which is the hexi, was the I format, and like hex and binary is 1001 or yeah. But I guess that's just how much bit we're storing for the method.
No, this is just actually a number. So here, 13 is a number, and 23 is a number, so decimal there, registered number. And
Mhm.
this is the immediate bit, 16 bit. Whatever 16 bit here, you're given this. 16
Oh,
bit
okay.
here. So it's given to you.
So, then
So-
if we wanted to figure out the format, we just have to look at ORI, and that's how we
Yes.
figure it out?
Yeah, so you go to the
Okay.
sheet, and see what ORI format is. So here, you go back here, ORI is RT first and then RS. And
Okay, I see it now. Yeah.
And this is I format, so you should I format. For I format, you go here, I format. What is this? See, the first is opcode, 6-bit, and then 5-bit RS, and then 5-bit RT, and then 16-bit is
Yeah,
immediate.
that's a 16-bit. Yeah.
You get that? So when I practice some example, it will be very clear
Yeah,
how you do it.
Yeah, I'm starting to understand it.
Yeah, it takes a little time, but you'll understand. So you will be given, for example, that we go back to our, let's say this ORI 23, 13, whatever. So any random number. Let's say
Okay.
we are given, let's say ORI like this. Actually, it's not a capital, it's small. So you're given this, and then a target register 23 or 13 or OX 23D4, whatever. So that's the hexadecimal number, okay? So it's given. Now, so this is MIPS code. This is MIPS code. Okay, now our job is to translate this in machine code. So first thing you need to see, what is the operation here? ORI. What ORI stands for? You go to sheet here. Then you see ORI is actually OR immediate, and that's I format. When you go I format, you look at the format, I format. So the first is opcode, and the next is RS, and then RT, and then immediate 16-bit. Meaning that whatever you are given here, so this is opcode, and this is opcode, and this is RT or RS. I think it's RS or RT. According to the here, according to the sheet, so this is RT and RS. RT first and then RS. So that's RT and that's RS. And that's the immediate field. Immediate 16-bit immediate field. So last. So how do you convert it? So you see ORI, which is the OR immediate. So what is the opcode for that? So if you go back to the sheet, and see opcode for ORI. So this is the ORI. So there is no opcode, so it's 0 actually. So opcode is 0, but the function code is D hex. Function code is D hex. So opcode is 0. So you put 6-bit 0 here. And then this RT, this is 23. So you go back to the sheet again. And here, so it's 23 is register 23. So register 23, if you go back to the table here, 23, decimal 23 actually stands for 10111 for 5 digit, 10. So 10. So that's actually should be in machine code. Machine code, this is here actually, 10111. And then here will be the 13, the RS. So for 13, if you go back to the sheet again, you don't have to convert it on your own. It's given here. It says 01101. 011. Represents. So that's 13. And then this is hexadecimal. 4 is what? 4 is 0101, isn't it? No, this is 4, 0100. And then you have D. D is in hexadecimal. A, B, C, D. 10, 11, 12, 13 actually. So 13 was this actually. So it's same as this. 13. And 3. 3 is what? 0, 0, 1, 1. And then 2. 0, 0, 1, 0. So this is 16-bit, 16-bit immediate field, and this is your RT, and this is 5-bit RS, 5-bit, 5-bit, 16-bit, 6-bit, 6-bit opcode, whatever. So for URI, $23, $13 register, and OX 23T4 equivalent to, can write like this, 0, 0, 0, 0, 0, 6 zeros, 0, 1, 1, 0, 1, continue, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, and 0, 1, 0, 0. That's it. I think it's in online. It's just to continue. So exactly same thing. This is a machine code and this is MIPS. Now, so that's one way from the MIPS code to machine code. But then you can do a similar way from machine code to MIPS code. If you're given a machine code, now they ask you to transfer it to MIPS code, you have to separate this bit. Just look at the PowerPoint, maybe we might have some example there. So this is how they do it from MIPS code to machine code. Other operations like LUI, it's also immediate, add is R format, and if you have I, that's immediate format, and jump and link, that's the J format. Still I format, so you have this. And an example, load word. See, load word is actually I format, but there's no I here. So you got to go back here and look for that load word command. So load word here, LW, is I format. So from here, you figure out what format is this. See, it's not always like I given. So this load word is I format, but it's not given I. So it's I here. So you need source and target. And this is I format, so 16-bit. And this 23 hex is the function code. This last bit, 23 hex. So immediate is there, so you don't need to worry about hex code here, function code. You don't need function code here because it's immediate 16-bit. But for our format, you need a function code here.
Professor,
Yeah.
I had a question about this example. How did, so on the sheet, the ORI,
Mhm.
hold on, sorry, let me open the sheet again.
Yeah.
For the opcoder function, it shows D hex.
Yeah.
How did the opcode turn into 6 zeros?
Oh, because it's 0. No, opcode doesn't say actually D hex. Actually, it's function code. So for ORI, see, ORI is opcode is missing. You see that? Opcode is missing, but the D hex is hex is the function code.
Oh, I see. Okay.
Then you understand this is like a I format, and D hex is the function code, not the opcode. Opcode is 0, so first one is opcode, and then slash that. If you don't have this 0, then is second one is the function code. And we already know that this is a I format from ORI, so it's I format is 0, 0, 0, the opcode. You see that in here. And this one, see, load word is not 0, 0, 0. See that load word is not 0, 0, 0. So let's look at the load word command, and then you can see that load word I format, and go look at this. So 23 hex here, the function code. Function code is 23 hex for the load word, and 23 stands for that number. You see that what is this table? 23 hex. This is hex. This is 23 here. 1 0 0 0 0 1 1. So 1 0 0 1 1. We have that 1 0 0 1 1. So that's the function code hex. Okay. 23. And the other example here. Yeah, 0 0 1 1 0 1. What was the number? So this function code is, or opcode is VARI. Yeah? 0 0 1 1 0. What is the number here? 1 8 12 13 actually. So in here, how did they do that? So VARI they put 0 0 1 1 0 1. VARI.
Is it because it's a D hex? So we look at the hexadecimal for D and then look at binary for it?
Yeah, I think, yeah.
So it wouldn't be 60, but actually it'll be on the sheet. I think it says.
Yeah. For add is 0 0, but for VARI is not 0 0. Yeah, that's right there. VARI is D hex.
D hex, yeah.
So the D hex, it's A, B, C, D. That's 10, 11 to 13 actually. Yeah, 13.
Yeah, so I guess, yeah. So it wasn't 6 zeros, I guess.
No, it's 13. So here, that's wrong. Okay. Use the pen.
I mean, we could just change ORI to add.
No, we don't have to. Just here will be 13. 13 is what? 0, 1, 1, 0, 1. Yeah. Put another 0, 6 bit. So put another 0 there. So it should be there. This. The D hex. Not 0, 0, 0. If it is add, like addition, then you put 0, 0, 0. Because that's what you have in addition, like over here. For add, you have 0. The opcode is given 0. And this is the function code. But for ORI, see, the function code doesn't make any sense. That's actually opcode. I was wrong. So if you don't have this opcode, then the next one, like here, 4 hex, means that's the function code or opcode actually. Because immediate, you don't have the function code. You don't need the function code because you have 16 bit immediate, but you need opcode. So this is actually opcode, not the function code. Remember that. So the D hex was actually opcode. And 23 hex also opcode, if there is no opcode actually. If it is both there, then first one is opcode, second one is function code. But if it's 1, that's actually most of the time is for immediate, and that's actually the opcode, not function code. Function code requires if the opcode is 0, because you see that the add are format, add u also are format. But then how do you know which one is add, which one is add u? And also are format. You see that? So whenever you have that add I, you have both. You have opcode and function code both. And opcode most of the time is 0. See that? For R format, opcode is 0. Meaning that if 0 is not there, that whatever you have, that's opcode. That's not function code. Okay, so it's clear now. So that's the way you translate the I format. But then we have J format. Learn that too. Load word is actually I format. LUI is I format, of course. And then should be some example for J format. I format, conditional I. And have ship less than. And here is the calculation of branch target address, BTA. Address of an instruction to jump to if condition is true. So for the jump, we need to calculate this BTA, the branch target address. And the formula here is like this: address of branch instruction plus 4 plus I shift left, like 1 shift left 2 bits, sign extension to 30 bits. Example given. So BTA, you have to have the address of the branch instruction plus 4 plus offset. And that will be your BTA. And we need that for the jump. So that's the last one, like jump format. There's some details, distribution. I think I have some notes on this, probably we'll look at it next class. They will look at next class for the BTA calculation and how the jump and link thing works like this: opcode, then 26-bit jump address. Okay, we'll look at it in the next class. We're tail end of the course. Just try to learn this, go through these slides and try to understand the green sheet. Green sheet is important. So use this format from here, this code from here, and then I use this register name and number, use call convention number from here, and then we translate it into machine code. Okay, so we'll talk about that more in the next class about this. And then once we finish it, then we'll have an assignment. All right. So I think we'll stop here and see you in the next class.
Thank you.
Thank you.
Thank you, Professor.
Mm-hmm.